All right, so we're going to talk now about introduction to organic compounds. Okay, so this is one of the nomenclature chapters. There's not much for me to teach in the space of nomenclature. Uh, I don't know if this is still the correct section, but read the relevant nomenclature section in your textbook. Alkanes, cycloalkanes, alkyl halides, ethers, alcohols, amines, IUPAC, and systematic naming systems. So compounds are classified into different function groups. Alkanes have carbon and hydrogen, hydrocarbons. There's no pi bond. Simplest molecule to name. Straight chained, which just means it's not a cyclo. It doesn't form a ring. One, two, three, four. This is butane. Okay. And like you can look up or like when you do your reading for nomenclature, you'll figure out that one is methyl, two is ethyl, three is propyl, four is butyl, butane. Anyway, so on and so forth. 2,3 dimethylbutane. So one, two, three, four carbon chain. There's the methyl coming off the two and three position. Cyclohexane, one, two, three, four, five, six. Six corresponds with hexane. Cyclo corresponds with the fact that this is a ring structure. Okay. Again, these are just some examples. They are, like what I'm going to cover in this video in the space of nomenclature is by no means exhaustive, and I really need you guys to read the textbook for this one. I'm not a huge fan of nomenclature. There's not really much to teach here. It's all just memorized. It's all rules. Okay, alkenes, one or more pi bonds. So pi bonds just when we have an extra line. Either that's a double bond. Um, we could have another double bond here. Specifically, alkenes are when we have double bonds. Alkynes are when we have a triple bond. Okay. All we're doing is we're changing the ending a little bit from ane to ane to ene. For triple bonds, yne, yne. That just corresponds with the name, right? Alkane, ane, ane, alkene, ene, ene, alkyne, yne, yne. Well, isomers. So constitutional isomers have the same molecular structure, but they are forming different structures. Sorry, same molecular formula, but they're forming different structures. So here I have one, two, three, four carbons, one, two, three, four carbons. I have three, six, seven, eight, 10 hydrogens. I have one, two, three, four, five, six, seven, eight, nine, 10 hydrogens, right? Same amount of carbons, same amount of hydrogens, different connectivity, right? Okay. Structures of alkyl halides, alcohols, amines, and ethers. Alkyl halides are carbon chains bound to a halogen, right? So I have a carbon chain, I have a chlorine, iodine, bromine, fluorine, any of the halogens. If you look on the periodic table, the second group from last, or yeah, I guess first group from last, there's the noble gases, and then there's the halogens, right? The halogens are halides, alkyl halides. Alkyl group, halide here. Fluoroethane, 2-chloropropane, right? So all you're doing is starting by using the prefix of that corresponds with the halogen, and you're telling me what position it's at. You don't have to do it for the first one because if you don't do it, it's assumed that it's at a one position, right? Okay. Um, yeah, I mean, you can just recall these. I don't think they're particularly relevant to naming. This is just to say that I is, when bonded to carbon, the weakest and longest bond, versus F is the shortest and strongest bond. Okay, classification. So carbon classification. CH4 is methane. When one of those H's is replaced with an R group, R is just a stand-in for carbon. Okay, so it just means that this first connection is carbon, and the connections that carbon makes to other stuff can be anything, right? This R just means this first connection is carbon, and we have a ton of other stuff. Methylene means we have two R groups, so carbon, carbon, whatever, whatever, right? So two connections to carbons, two hydrogens. Methine, three, quaternary carbon, four, right? So primary, secondary, tertiary, quaternary just refers to the amount of carbons that are attached to it, right? Methane has zero, primary has one. Again, R groups are just carbons. The reason why we say it's R and not carbon because we have a carbon, but it's not just a carbon. It's a carbon attached to a bunch of other stuff. We just don't care about the other stuff. This R is just to signify that this bond from this carbon here, the first thing this is bonded to is carbon. Okay, secondary, two R's, tertiary, one, two, three R's, quaternary, one, two, three, four. Cool. It's just important to note that if I had a double bond here, I'd still count this as one. If I had a triple bond here, I still count this as one. Okay, so we don't count multiple times for primary, secondary, tertiary, quaternary. Okay, classify all the carbons in the compound. So, pause the video here. Make sure you understand why these carbons are classified the way they are. It's pretty okay, pretty easy to go through. Okay. Um, okay. Alcohols, ROH, tetrahedral geometry, always sp3 hybridized. Primary alcohol just means we have one carbon attached to the alcohol group. Secondary means at this carbon we have a carbon here and a carbon here. Tertiary, at this carbon we have a carbon here, a carbon here, and a carbon here. So it's exactly the same as the trends of this, except when I talk about this carbon, I'm specifically talking about this carbon has to be attached to an OH, right? I can't get a quaternary alcohol because I would have to make five bonds and a hydrogen, which we know does not happen. Okay, ethers. So ethers are named as an alkane with an RO substituent. You can replace with a YL with oxy, ethoxy, ethane, methoxy, ethane. Again, this is by no means an exhaustive, boot camp on naming, so please consult the textbook. The general structure of an ether is when we have an O and R on both sides. These R's don't have to be the same. This could be R1, this could be R2. I should have written it like that. Tetrahedral geometry. The O is sp3 hybridized. R groups can be identical, symmetrical, or different. Unsymmetrical, right? These R groups are the same. These are different. Perspective drawing. Amines contain nitrogen, CN single bond. Classification, primary amine, 1 R, secondary amine, 2 Rs, tertiary amine, 3 Rs, quaternary amine, 4 Rs, right? So the degree, primary, secondary, tertiary, quaternary, just really refers to the amount of carbons that are connected to something, right? In all cases, there's slight caveats to that, right? But it's essentially just revolving around that concept. Okay, so this is kind of an important concept. So rotating around a carbon-carbon gives conformational isomers, right? If you think about a wheel or like on a car, right? If you have an axle and you have a wheel on both sides, you can rotate, right? If I had two things, then I wouldn't be able to rotate. This is why, like, an axle is just one thing, right? So with that, you never rotate carbon-carbon double bonds or carbon-carbon triple bonds. Rotation does not change the molecule. So there's an important difference between conformation and, different molecules. So this is something called a Newman projection. And, I would, again, get pretty comfortable drawing these. I'm not going to go exactly through drawing these. I guess I could here. So this hydrogen here is coming out of the plane, right? So with that, let's say I have this phone is the back, okay? So this corresponds with the one carbon, this corresponds with this carbon, this corresponds with the two carbon, this carbon, okay? So if I'm coming into the plane, or um, if I'm coming into the plane here, you can see that it's coming at me, okay? If I turn to the side, you can see that this is to the right, versus if this was coming out to me, and I turn to the side, this is to the left, right? So the whole point of this Newman projection is 1, 2. It used to be like this way, right? Horizontal. And now I'm turning this around. And when I turn it, you can see how if this is coming into the plane, if you turn it so that I have now moved this from here to here, you can see that this on a wedge will go to the right. This on a dash will go to the left. And this is specifically when we're looking this way. If we look the other way, we'll see that's actually the opposite. This will be on the left and this will be on the right. And, look up some videos on visualizations of this. It's pretty important to being able to draw this structure. When you do practice problems too, I think it'll become a little bit more obvious. Okay, so there's a staggered conformation and an eclipse conformation. Staggered basically just means that all the groups are spaced apart. Eclipse is just when they're right on top of each other, right? So why is staggered more stable? It just has to do with delocalization of electrons by the overlap of a sigma with an empty orbital, with the empty non-bonding orbital. It's just basically staggered conformations are stabilized by something called hyperconjugation, and I think it just makes sense in general that you want to spread out molecules, right? Like you don't want things to be on top of each other, right? Just intuitively, that doesn't make sense. So we want them to be spread out as much as possible because we get, repulsions or interactions between these two groups, right? Or run on top of each other. Okay, rotation around a carbon-carbon bond. So this is the potential energy diagram, right? So the lowest energies will be in the stable conformations, right? These will be the same because these conformations, you can see like just they look the same, right? These will be the greatest energy and they'll be the same values because you can see they look the same, right? And we only really care about these peaks and these troughs, right? Everything between them is just, slowly rotating, minimum, maximum. This corresponds with degrees of rotation. Okay, cool. Um, okay, so this is an example of a molecule where you have different Newman structures, right? These are all hydrogens, so it's pretty easy to draw ethane, right? Because you don't really have to care much about which goes where, what does what. They're all hydrogens, right? So for this, you rotate at 60 degrees and you get this structure. Rotation around a carbon-carbon bond, butane. There's something called gauche staggered, which is less stable. Anti-staggered is the most stable. So before you saw that these two structures had the same energy levels, right? Because these are all the same. These are all the same. However, these are slightly different, right? In this structure here, you have two possible overlaps, right? You could overlap a CH3 with an H and a CH3 with an H, which correspond with these two, or you could overlap a CH3 with a CH3, right? Um, so it's important to note that there's slight differences. Oh, so sorry, I misspoke. Those don't correspond. It's important to note that, the CH3 overlapping with the CH3 is worse. It's the highest energy. It corresponds with these energy levels. Um, and, it's just the two biggest things overlapping is something that you never want to happen, right? So the two things that make something unstable are, first of all, things overlapping and the size of those, okay? So we get something called steric strain. So this concept of something called sterics basically just means like a lot of stuff in an area. Okay. And we don't want a lot of stuff in an area, right? If I already have stuff in an area, I don't want to put more stuff in the area, right? This is just unstable, right? Like things don't want to be right on top of each other. Things don't want to share the same space, right? They want to spread out. So steric strain just has to do with repulsion between the electron clouds of atoms and groups of atoms. So it's more of a precise definition, right? Okay, drawing a line structure from a Newman projection. So you should be able to go from this structure to this structure back and forth. And again, this will require a lot of practice. But if you consult, your textbook, they'll give you a little bit more advice surrounding it. In the interest of making these videos not too long, I'm not going to go through specifics. Okay, conformers of cyclohexane. So cyclohexane is the most stable cycloalkane with a bond angle of 111 degrees. So there's no ring strain. So when you have six-membered rings, you have the optimal ring size. Anything greater than that is ring strain. Anything less than that, ring strain. So this exists in something called a chair. Again, you should be able to get comfortable with drawing the structure. Um, Ring flip is also something you should be comfortable with drawing. We have two positions on chair, axial and equatorial. Okay, so these axials are really easy to draw, right? Up, down, up, down, up, down. These are a little bit harder to draw. Okay, so this line is going to be parallel to the line that's one apart from it. Okay, so this line's here, one line apart, it's parallel to this. One line apart, it's parallel to this, right? Because these two lines are parallel. This line, one line apart, it's parallel to this. One line apart, it's parallel to this. And this direction, if you're not really sure which it is, you can draw a little arrow on it, and it's very easy to see this is up and this is down. I think it's in general easy to see for axial if something is up or down, and then equatorial is just, whatever this is not, right? So at any given position, you can only have one position that's up, one position that's down, one that's axial, and one that's equatorial, okay? This is just a rule. So this is something to memorize. Newman projections. You can draw Newman projections for uh, cyclohexanes. This is how you would draw it. Again, I'm not really going to go into the specifics associated with it for now, but this is something you should, grow relatively comfortable with doing. Cyclohexane is stable because all hydrogens are staggered, hyperconjugation plus minimal steric strain. Cyclohexane has almost no ring strain. Okay, conformers of monosubstituted cyclohexane. So ring flips are equivalent, they have the same energy. Theoretically, A is more stable than B because of sterics. So this is an equatorial position and this is an axial position. All axial positions become equatorial, vice versa in a flip. So at each point, you just flip axial and equatorial, you flip axial and equatorial. You can redraw the chair like this, but it's also correct to just take whatever group is up, whatever group is down, and just flip them. So the CH3 becomes up and this just red line becomes like down like this. Um, so the R groups in the axial position are not favored because of steric strains. So the larger the group, the greater the effect. This is just to say that, if I have tert-butyl, which is just really unstable. And I have three OHs, and I can arrange them in a way such that I have one tert-butyl axial, but then the rest of the groups are equatorial. This is so unfavorable that you'll always just put the bulkiest thing on equatorial and you don't care about the rest, unless they're really close in values, right? Like, for example, like, oxygen or OH versus CH3, if I have five OHs, that'll be placed equatorial or axial, sorry. If I place the CH3 equatorial, then I won't do this, right? Because 5 times 5.4 is a higher number than 18, right? But tert-butyl, you'd need to have, like for OH, you'd need to have like, I don't know, 9,600 of the OHs, which is just, it's not going to happen, right? Okay. Conformers of disubstituted cyclohexane. So cis means both substituents are on the same size, both are pointing up or both are pointing down. Trans means opposite sides, one is pointing up, one is pointing down. The conformer with most equatorial substituents or larger equatorial substituent is more stable because of less steric strain. Okay, so up and down on this kind of structure are pretty easy to identify, right? These are cis to each other because they're both on wedges. These are trans because one is on a wedge, one is on a dash. Well, these are trans, cis, cis, trans, trans. Okay. For this, we don't care about equatorial or axial. We only care about direction. So this is down. This is down. They're cis. This is up. This is down. They're trans. I could have equatorial up here, and this equatorial up relationship to this would be cis. So I don't care about axial equatorial. All I care about is up or down. So even though the conformation puts two substituents axial, it's more favorable since tert-butyl can never be axial due to steric strains. This is what I was talking about earlier, right? We always put the bulkiest thing on equatorial first, unless they're really close in value, right? So with that, if you ever see a tert-butyl, you're always going to put it equatorial, and then the rest are just going to be wherever they're going to be. Okay, cool.